thiionite, that means iron oxide associated pool, as you can see right here. Cations like magnesium, sodium, zinc, potassium, and so on. And the anion side has phosphate, to some extent carbonate, and some accessory anions, which could be hydroxyl, fluoride, or chloride. Now, depending on how you look at this mineral, the organization of this columnar hydroxyl is here, and these sites are often replaced by carbonates. You can see very right is the specific symmetry of P63 and lattice structure of apatite. If you take a very detailed high resolution TEM of this material, you can see very nice lattice fringe, as you can see right here, zoom inversion, as well as selected area diffraction, SAED, crystalline material. So in this aquifer, you can see both very crystalline material of phosphorus mineral in the apatite form here, and as well as some amorphous phosphorus that does not form, which is not shown here. We can do FTIR, Fourier transform infrared spectroscopy, and look at the composition of this material. Now, the nano FTIR, which is a very small scale, which is depicted in the illustration here, what we do is that we have a laser beam and which have a penetration capacity of about 10 nanometer or less, and it can sputter the material from the surfaces or look from the surfaces and then find out what material the particular sediment is composed of. So, as I mentioned before, it's largely of sediment material. So, how that sediment material is composed of apatite or phosphorus mineral shown by these processes, as you can see, largely of apatite material. So it's clear on this rock, on this aquifer material, the sand particles which contain the iron oxide coating has apatite as a major phosphorus material. Now let me show you about the redox channel of iron reduction. So what happens is in a biological system, redox potential or how much energy they can get out of the redox process is something that controls the process. Now, if you look at the oxidation and redox potential of any system, for example, here, the lactate oxidized to acetate at the expense of oxygen turning into water, you can see the process of electron transfer. So that gets one extra electron, goes to iron oxide, and then the key part of iron oxide reduction is that iron 3 becomes iron 2, which is largely soluble. So that causes a release of iron to the aquifer. So release of mineral in which iron was present also causes release of phosphorus in the system. So the obvious is that aquifer that goes in anoxic cycle can release a whole lot of phosphorus from there. So now let me explain how we can see that in oxic versus anoxic system in a controlled environment. In the y-axis here, you see a normalized concentration. In x-axis time is in log scale, just keep in mind here. So if it's an oxic environment, we can see some of the pool that is sorbed into the system change significantly, right? Change ratio decreasing means it's utilized by organism. Now, if we change to anoxic environment, what we see is a other pool, which is iron oxide bound pool used by organism. So the system could completely shift from one pool to other pool of preferential uptake of phosphorus by organism. And that makes a huge difference how the aquifer phosphorus system work out. Now, let me go back to biological uptake control phosphorus cycling. And now I'm showing the same figure I showed before. Now, with the number here, these are phosphate oxygen isotope values. What is the key part of this number is, let's look at the anoxic zone. As you can see, anoxic zone isotopes are quite different than everything else around. Now, the question, what does this mean, is that in anoxic zone, the phosphate oxygen is completely equilibrated with water oxygen. So that only happens, there's a significant biological cycling into the aquifer. What does this mean? It's certain part of the aquifer where there's a whole lot of microbial processes happening, it's changing the isotope composition of phosphate as well. So one way of confirming that biological cycling of the system in the aquifer. Now, there's a whole lot of chemical reaction and reactive transfer model has been developed and work for a long time. But as you can see, phosphorus sorption, protonation, deprotonation, sorption, desorption, and very last, as you can see here, is vivianite precipitation and dissolution reaction with the kinetics terms are included in this reactive transport model. As you know, Parkhurst, he is working on this project for a long time. Now, by this reactive transfer model and using isotope, we can look at on the very left here how much phosphorus can come out of the sediment as a function of pore volume. So if you look at a simulated base case model, which is solid here, these are data points, versus the phosphorus sites 2 times magnification, like if you increase by 2 times in phosphorus reaction, goes up here. So from base model, we need a significant revision to get into this actual data. So somewhere, we need to work more to get fit into this. Now, and this in between comes like about 1.4 to 1.6, and as well as the pH change system here from 7.42 to 5.78, and we get close. Now, based on this modeling, all the reaction and equilibrium reaction as well as kinetic reaction, as it's shown here, we can figure out how much phosphorus is actually coming out or oozing out of the aquifer. Here in a phosphorus kilogram per year, as you can see, from almost 500 at the highest 1,500 kilogram over time. 1940, that's where the base started. About 60, 65, the base ended. And then the aquifer is still releasing a whole lot of phosphorus to the pond. So vivianite mineral, apatite mineral formation in the aquifer are causing various processes that slows down and gradually releasing through this aquifer. Now let me go slightly away from here in radiometric age dating. So in one of the projects, we are working on very long half-life krypton and chlorine.
Can you Show your
And
slides,
with
sir. Next slide, sir. You are not getting your slides. Slide is not matching with your deliberation, sir.
oh,
Yeah. Radiometric age now. Okay.
oh,
Yeah.
perhaps there's a
Okay.
lag, right? I'm presenting, it's not coming when I present. Okay.
Okay.
So here I'm showing that radiation is dating using krypton 81 and fluorine 36. This is not the Cape Cod aquifer I mentioned, but using those very rare radioisotopes, we can date the aquifer material as old as more than 1,000,000 years, as you can see here. Fitzperry Wall, this is a kilo year, so this is 1,000,000 year. We can go as old as millions year old. So this method have quite been used in various parts, especially in desertic water, aquifer water, where the water age could be much older. And this is a case of Egypt, where the aquifer water is as old as slightly more than 1,000,000 years old. So this is a different cases though, but still using radioisotopes to find out the ages. Now let me make very short conclusion here. Phosphorus transport in aquifer is controlled largely by redox processes. Once there's a phosphorus is the nutrient, and then requires a whole lot of processes, and life is present there, so they start to recycle through redox processes. Now, phosphorus transfer model in hydrogeology requires a more of a redox process inclusion in reactive transfer model, which is more and more common, and isotope provides a strong biological cycling evidence in aquifer. That's all. Thank you.
Thank you, Professor. Please stay in touch. If there is any question, please. We are getting only 2 questions. If anybody interested, please.
Thank you. Very nice, very informative presentation, Professor Dev sir. I am Kaviraj Paudel from here. So you described and you carried out in-depth investigations regarding the phosphorus and basically the geochemistry part in groundwater and other water bodies. So you know, in our case, basically in our Tarai region, our groundwater is polluted due to arsenic contaminations. So do you think the nature of mobilization of arsenic and these phosphorus is similar or not? So what you suggest to us to investigate the arsenic mobilizations from materials to groundwater? Thank you.
Very good question. Thank you. Thank you for asking that. So the arsenic and phosphorus, the anion chemistry are very similar. Redox chemistry are different. Now, what is important is that the redox chemistry of iron oxides in the aquifer control both phosphorus and arsenic fate. So what does this mean is if the redox chemistry drives the iron reduction, making iron 3 to iron 2, then whether it's a phosphorus or arsenic, that releases out of aquifer. So I think just measuring the redox chemistry of iron could provide you a very good insight of where the arsenic is leaching, or what's the leaching potential of arsenic in an aquifer.
One more question, please.
Thank you very much. Your nice presentation. I am Ashok Sigdel and working in Department of Geology, Tirchandra Multiple Campus as a lecturer. And one one question is, based on your research, how did the iron oxide come into the aquifer sediment based on your research? And another one is, how can you apply it in context of Nepalese scenario, especially in the Kathmandu Valley disposal site? Thank you.
Thank you, Sigdalji. So where the iron oxide come, it is unclear the origin, but this is the earth material and the abundance of elements and the oxidation potential of the earth surfaces creates iron oxide. So the environment is favorable for formation of iron oxide. The question is what form, what mineral composition and crystallinity of iron oxides are present in an environment. So that's the key question. So if the redox chemistry is driving any of the element mobility or fate in an environment, so iron oxide is a proxy to study. So I'm not quite sure about the chemistry of aquifer in Kathmandu or any part of Nepal, but if you were to look at that the redox chemistry of iron, it tells a whole lot about the fate and mobility of elements that associate with iron oxide. Many of the aquifer, which are more of a clean aquifer, like in Tarai, the sediments are largely silicate based, right? So there you expect a significant role of iron oxide.
Okay, thank you, Professor, for your nice answer. I would like to call President Dr. Dinesh Pathak will address you.
Thank you, Professor Dev, for accepting our invitation and delivering your great work among all participants, even within the short notice. And I highly appreciate for your presentation, even if you are at the midnight and you have a woke up through the sleep. And I wish you have a nice sleep. Thank you very much.
Thank you so much. Bye, everyone.
Okay. हाम्रो next presentation पनि online नै छ. Mr. A.K. Tiwari, groundwater contamination and associated risk to human health. यो चाहिँ एउटा केस स्टडी रहेछ कोल माइन एरियाको. अनलाइन हुनुहुन्छ, उहाँलाई व्यवस्था गरौँ त अनलाइनको. JNU. Okay, please make him online. अब यो अलिकति टाइम कन्स्टेन्टले गर्दा विदेशीहरु चाहिँ अनलाइन हुनु छ, उहाँलाई हामीले अलि टाइट गरेन. यहाँ चाहिँ हाम्रो नेपाली प्रेजेन्टेटरले अलिकति टाइट गरौँला है साथी.
Good morning, everyone. Can you hear me?
Yes, we are hearing.
Yeah.
Welcome.
Good morning and to everyone. Thank you for inviting me. My name is Ashwin. Different element. For example, if you see the Gangetic belt is contaminated with the arsenic. If you see some places we have contaminated with chromium, especially Kanpur, which is industrial area. We have also problem of fluoride. Many states are suffering from the crisis and risk of the fluoride contamination. Nitrate is common contamination in everywhere because we are doing lots of agriculture activity and we created lots of issues with the nitrate as well. And if you see the overall picture, so
maths. Okay.
Okay, so I'm going to minimize it because every time I have to minimize, I was discussing this topic
Okay.
about the Indian.
Okay, it's okay. Go ahead.
Can you see the slide? It's changing or the same slide?
This is the second one, and which one you like to show us? Third one or the second one?
So it's saying the percentage shares of groundwater for irrigation.
It's India's water maths is the second one, and third one is the bar chart, I think.
Okay.
Yes, this one is the bar. Total in water use.
Yeah, so now
Okay.
I'm here.
Yeah, okay.
Okay, so I have to change every time. Minimize it and change it. I don't know what is the issue. So if you see here, if you see the budget, and if you see the Uttar Pradesh, we have a much annual water use because of the population is highly populated state in India. But if you see here, in percentage which is going to use for the irrigation, if you see the Punjab is highest, Punjab and Haryana, as compared to Uttar Pradesh. Why? Because we use lots of groundwater resources for the irrigation purposes. And if you see India, the extraction of the groundwater is double than China. And more or less population we have similar, little bit higher. India have now is higher population. But if you see the extraction of the groundwater is double than China. And that is very much concerning for us. And if you see the per capita storage, we are very less. We have less storage, we are withdrawing a lot, and we are suffering from the water depletion as well as groundwater contamination. Can you see the next slide? Now?
Yes. Okay.
Okay. So more focus on the mining areas because most of the mining area in tribal areas and there is no freshwater resources for drinking purpose. And if there is freshwater resources, it's very deep. So people is totally depend upon the water which is contaminated with different element, especially contaminated with the iron, Mn, nickel, high TDS, total hardness, and these things. And due to the mining activity, we're creating lots of issues in the mining areas. So my project was to understand the seasonal variation in groundwater contamination, what is the impact of mining on water resources, and what is the risk to the local population there. So if you see water crisis, so it's very common pictures in the mining area when you go. Lots of people have a crisis to have a, they have to forcefully they have to come out to collect the water for their survival. It's not easy. If you see here, lots of people coming, they have a permanent solution. So it's indicating that it's not one day job. It's everyday job. They have to come out, they have to collect water and they go to home for cooking and other things. So it's very common. If you see here, is pictures from the hand pump from the coal mining area close to the mines. If you see here, high concentration of nitrate you can identify with the help of the precipitation. And you can see the color of the water as well is reddish color, that indicating that the enrichment of the iron. And there is also problem with the open wells. They are contaminated with different suspended particulate matter and other things. So just I'm going to move to the study area. So it is a study area which is located in the Madhya Pradesh district, is Umaria coalfield. And we have selected the Umaria coalfield to assess the seasonal variation in groundwater chemistry. And this is the under the Southeastern Coalfield Limited. And we have collected total 100 sample and 50 sample from the same location in the pre-monsoon sample and 50 sample in the post-monsoon season to understand the seasonal variation and how chemistry is going to be changed. And we have observed the water level table is going to vary from 1.9 meter below the ground level to the 11.12 during pre-monsoon season and 1.3 to the 9.7 in the post-monsoon season. The geology of the area is mostly suprabracker, bracker formation, talchir and metamorphic. The study area mostly belong to the bracker formation, which is consist from the medium to coarse grain sandstone, shale and coals. And we have analyzed the pH and electrical conductivity at the field using the PHEC meter, turbidity with the help of turbidity meter, major cation and major anion we determined with the ion chromatography, and metal we have analyzed using the ICP-MS. So result and discussion. So we compare both the decision, and we have observed how much water is going to be exceed the acceptable limit. And if you see here the turbidity, if you see here the sulfate, if you see the magnesium, calcium, total hardness, and TDS is more concerning parameter for us. Luckily, the coal field is not have a acid maintenance problem. The pH is within the balance. It's not going to be below the 6.5 or less than that, much and much, because of the carbonate buffering is there. So pH is going to be maintained in the study area. This is the TDS map of the area between the pre and post. If you see the little variation in the pre-monsoon season, the concentration going to be higher. The TDS concentration is more in pre-monsoon season as compared to the post-monsoon season. And if you see the reddish color, they are very close to the mining areas. We observe the high concentration of total dissolved solid, which the samples are very close to the mining areas. Similar, if you see the sulfate, here if you see the sulfate concentration is more in the pre-monsoon as compared to the post-monsoon season. And what is the reason behind the sulfate concentration in the groundwater of the coal mining area? Because of the pyrite dissolution. So there is reported in the coal seams, we have one thin layer of the pyrite, and due to the pyrite dissolution, we have high concentration of the sulfate, also iron. Now you can see the total hardness, which is more concerning for industrial purpose and other domestic purposes. We have high concentration of total hardness, and it belongs to the hard to very hard type of water due to the high concentration of calcium and magnesium in the groundwater of the area. Now we have also tried to understand the water type and hydrogeological phases using the Piper diagram. It's the diagram which is helped to understand what is the water type, what is the possible source is there. So you can see most of the sample is plotted in the calcium magnesium type, and some samples plot in the calcium, magnesium, and chloride and sulfate dominancy, which is indicating that the two major type of water we have identified. One is the calcium magnesium carbonate type, and second is the calcium magnesium sulfate and chloride type. And if you see the ternary diagram here, most of the sample is fall in the no dominance zone, which indicating that no dominancy of calcium or magnesium or sodium potassium is a mixed dominancy between all. And if you see here, some sample is fall into the bicarbonate zone and some sample fall in the no dominancy zone. We have also plotted our data in a Gibbs diagram to understand the dominancy, whether it is dominated by the precipitation, whether it is dominated by the weathering, or whether it is dominated by the evaporation. So mostly majority of the sample plot in the weathering dominancy, which is indicating that the groundwater geochemistry of the study area mainly controlled by the weathering processes. Now we have plot some scatter plot to understand. If you see the plot number 1 between the calcium and magnesium versus bicarbonate, you can easily indicate that excess, if it's going to be in the line, which is indicating from the calcite dissolution or dolomite or something, but if you see here, the samples is plot excess towards the calcium and magnesium, which is indicating that the non-carbonate source. And if you see the diagram number 2B, which is calcium plus magnesium versus bicarbonate and sulfate, you can see here the good correlation. Most of the sample in the fall the line, which is indicating that the possibility of dissolution of calcium, magnesium, and gypsum. But in our study area, there is no gypsum is reported, and we have very poor correlation between the calcium and sulfate. This is indicating that the sample is with high concentration of sulfate due to the pyrite dissolution. And if some sample plot high concentration of calcium, magnesium because of the weathering of silicate or reverse ion exchange process going on there. Similarly, if you see here, some of the sample have a more dominancy of a strong acid over the weak acid in the study area. And if you see the plot calcium, magnesium versus the sodium and potassium, most of the sample dominated in the calcium and magnesium dominancy. And we have also tried to understand what is the possible source, and we have plotted the magnesium versus sodium versus calcium and sodium and understand which is more dominant. And we identify the study area geochemistry is mainly controlled by the both silicate weathering as well as carbonate weathering. And if you see here in the factor analysis is also indicating the TDS has good correlation with the bicarbonate, with calcium, with magnesium, with sodium, and bicarbonate have positive correlation with the calcium, magnesium, and sodium, and they have loading in factor 1, which is indicating that they are primarily controlled by the silicate and carbonate weathering. And on the other hand, if you see high loading of nitrate and potassium in the factor 2, which is indicating they are coming from the domestic and agriculture sources. So we have also analyzed the metals to understand the seasonal variation in the metal as well. And we observed that the iron and Mn is more concerning parameter. They have exceeded many samples, the limit of the BIS, also the aluminum. So we have to more further analysis of this. And then we have also compare this, our data, with other studies have already done between the major cation as well as the metals to understand. And we identified our study area slightly has low concentration of these elements as compared to the Jharia, Raniganj, Bokaro, and other coalfield. So luckily in this case. And then we have try to understand the seasonal variation between the ions. We have plotted the total dissolved ion, and we understand that there is no much seasonal variation. If you see, there is nothing much variation in the metals, very less variation, very less role of the rainfall, very less role of the precipitation in the study area, and they have more or less similar chemistry during the post-monsoon and the pre-monsoon concentration. If you see here, the concentration of iron is going to more and more. It's going to be greater than 1000 ppb, which is more concerning for the local people in the area as well as for the industrial purpose. And then we have tried to calculate the health risk using the UCPA formula to assigning the daily intake, assigning the weight and other things. This is the method where you can calculate the risk, possible risk to the health. And we have tried to calculate in 3 different age group, children's, and then for the male and female. And what we identified in the study area, children are more vulnerable as compared to the male and female, and we have to be more concerned about the children's health in the study area and require to the treatment before to the use of groundwater for direct utilization. And here is the comparative study of the metals as well. If you see here, metals, this is compared with the African, Bangladesh, China, as well as India. And luckily, if you see in present study area, if you see iron and magnesium average is very less as compared to the other mines in India as well as outside of the India, which is indicating these water easily could be treated for the different purposes. So the conclusion of the research was identified the pH was groundwater is slightly acidic to alkaline in nature, mostly is calcium magnesium carbonate type and calcium magnesium sulfate and chloride type. The measures we don't have identified any seasonal variation. More or less they have similar chemistry in both season, and because maybe the region because of the groundwater of the mining area they have no much variation in the ions. And then we identified the weathering of silicate, carbonate and sulfide mineral as well as the ion exchange and anthropogenic activity mainly controlling the groundwater geochemistry of the area. We emphasize that the pre-monsoon season have high risks to the health to the children because of the high concentration concentrated in the pre-monsoon, and they have compared to the male and female, they are in a risk and appropriate treatment is required. So this research is recommending that to reduce the concentration of the groundwater in coal mine area using appropriate technology to treat it, and then to supply for drinking and domestic purpose. So I would like to thanks to the funding agency and the mining authorities for supporting me doing through this research. Thank you so much.
Thank you. You too, Dr. Ashwani. Please stay connected. If there is any question, you can reply them. Anybody interested? I think there is no question. Everyone is satisfied. So I can give to Dr. Dinesh Pathak.
Thank you.
Thank you, Dr. Ashwini Tiwari, for your presentation, even in short notice. And I would like to request you to extend my thankfulness and regards to Professor Joshi. Thank you.
Thank you.
धन्यवाद सबै पार्टिसिपेन्टलाई पनि धन्यवाद हैन अब यो टाइम अलि सर्टेज छ प्रेजेन्टेसन को लागि अलिकति कर्टेल गर्ने हो कि टाइम 8 मिनट लेख्न चाहिँ 10 मिनट लेखेको छ तर 8 मिनट चाहिँ जति कोहीसम्म कम्प्राइज गर्न पर्ला र दुईवटा क्वेशनको हिसाबले जामला अब नेक्स्ट प्रेजेन्टेसन प्रेसिडेन्ट डाक्टर पाठकको हजुरको डीआर पाठक इज नट यू Okay, sorry, Pathak means I only know the Mr. Okay, I would like to call Mr. D.R. Pathak to deliver his presentation. Yeah, this is from dump site of electrical. Okay, go ahead, dear.
Okay, thank you, Chair. I think I've given to, as per program, I has given to the 15 minutes, but he reduced the 10 minutes. I'll try to do in the 10 minutes. Yeah, okay, my name is Tundiraj Pathak. I do research in university teaching by passion, but I'm mostly involved in consulting sector in the field of geotechnical and geo-environmental engineering and integrated waste management. I work in Southeast Asia and Africa, and currently I'm working in Asian Development Bank as a waste management specialist in Kathmandu. And today I'm coming here in the capacity of the president of Center of Research for Environment, Energy and Water, one of the partner organizations of this first Hydrogeological Congress. Presently, I'm also a member of this NHA. Today, my topic is, I'm not going to present all data and other things, just how this extreme knowledge, from all the experts' knowledge can convert to this open dump to at least the engineering landfill site to protect our groundwater and surface water and other things. I'm not talking about, in our presentation, you heard the extraction of the phosphorus, nitrogen, and potassium from the fecal sludge or from the solid waste. But at least we're talking here about you can convert this biodegradable or fecal sludge into the at least fertilizers before jumping to this extraction of the phosphorus and other things. Okay. This is the background. You see, we have a 293 municipality, and we generate almost more than 5,000 tons municipal solid waste. Out of 5,000, almost 60% is the organics, which degrade, which is the one of the leachate generating waste. And in Nepal, almost 50% of the total waste generated is not, collected. If collected, they go to the open dump without, the proper disposal or the proper treatment. You can see that the current situation. We burn the waste at the bank of the river, nearby the rivers, and we dump the waste not in the city area. You see, this is the bottom right side photograph is the Gosai Kunda. We have started to dump our waste, and we're degrading our water surface and groundwater from the in the mountain, not in the city area. Then we started our degraded water. That's at least we have to convert these open dump practices to at least to the engineer landfill with the knowledge of you people like hydrogeologists, geotechnical, or engineering geologists. Yeah. This is another case like even the fecal sludge. We declare the ODF. We, ask to the people to construct the septic tank. But this is the real situation of our septic tank. We use just the ring, and we just, change our like diffuse pollution sources to the point pollution sources. And the septic tank is one of the major groundwater polluters in these days, because these types of the open septic tank we prepare, there is no seal, and ultimately go to the converted to, infiltrate to all this contaminant to the groundwater system. I'm talking about how to convert this dump site to the engineered landfill site. But if you constructed the engineered landfill site, how we make this engineered landfill site to the finally the dump site? This is one of the example of the Sistole landfill site. In 2005, we constructed as a sanitary landfill site. But finally now, and after the 20 years, almost 15 years, we converted one of the vulnerable dump site, which is of the major sources for the contamination in surface and groundwater as well. And this is also another, our situation, because the disposal practice is not only related to the design, not related to the quality construction, but related to the operational practices also. Sorry, this is slow. I think I'm more smarter than your. Okay, this is how this, our Sistole is converted to the sanitary landfill, to the dump site example. You can see from 2003 to the 2022 photographs. And finally, we converted this almost 8 hectares land to the open dump site right now. And you can see here area. Initially, it was designed for just 2.5 years, nearly 3 years, to accommodate the around 150,000 tons waste. But finally, we disposed there more than 3 million ton waste over the last 15 years, and just this good sanitary landfill site is converted to the dump site and became one of the major groundwater polluter. Yeah, all of you know how this disposal site, the contaminants reach to the groundwater system without any proper barrier system, without good liners. If you have any liner system, ultimately go to the leachate to the groundwater, or you either go to the surface water. Therefore, I'm talking about how this open dumping practice can improve technically as well as in policy and some standards, enforcing some standards. The first thing, the open dump to the engineered landfill is not like a revolution. It takes time. This is the gradual process. But at the same time, you have to think not only in like design, not only in the operation, you have to think about from site selection. Right now, in most of our disposal site is located in the river bank. That's in the floodplains and other things. That's first of all, we have to think about where is the better site for the construction of these landfill site. That's why we have to start from the site selection. Then we have to proper design, proper construction, and then finally the operation should be as per our guidelines, what we have prepared for the sanitary landfill site operation. And at the same time, when we improve in technically, at the same time you have increasing the environmental standards as well as regulatory monitoring and like enforcement framework also. When you work together in the both sides, then we can convert this dump site to the engineered landfill site. I'm not going to talk about the detail how to do in this project, how to identify the site properly based on the different parameters. It's not only hydrogeological, not only geotechnical, or not only like an accessibility. All are the social and environmental consideration I have to think about the site selection of the landfill site. And after the site selection, we have a lot of rigorous assessment will have to be done. And finally, the consultation with the public. This is completely lack in our context, because normally we people, our expert or government side, want to hide with the public. When you go to the daytime, the municipal authority says, so we have to go in the evening to see the landfill site area or something like that. People come there and they obstruct, that's why that types of the, transparency doesn't work for the proper operation. That's why this consultation with the people is very important for the site selection as well as and the design of this also engineered landfill site. This is the site, how to choose the different types of depending upon the type of the land. The major things we have to consider to the design of the engineer landfill site is the first thing is how to develop this barrier system, proper containment system. That should be a good liners. That should be a good leachate collection system and gas management system. And of course, that should be a groundwater protection work as well as surface water control and subsurface migration of the landfill gas. The methane is one of the major gases we generate in the landfill site. And of course, the monitoring of the groundwater and leachate. Because we should have some groundwater monitoring wall in both in upstream and downstream side. And most of these, the monitoring wall are missing in even our sanitary landfill site, what we have developed. And site closure, post-closure plan is also very important. After 10 years or 15 years, even 20 years, the gas is being generated. Even the leachate is continuously generated, and you have to continuously monitor this groundwater well and as well as other leachate sources. And the major missing part here is that sanitary landfill, engineer landfill, whatever you say, everyone says like dumping site. That's so when you say the dumping site, you don't need any hydrogeological assessment, you don't need any geological assessment, you don't need any geotechnical assessment, and you don't design any liner or barrier system. And finally, all these leachate go to the groundwater system. And we are talking about our groundwater is not, fit for the drinking. This morning, our minister says the shallow groundwater is not fit for the drinking. This is the reason. But we are not talking about these things. Yeah, this is the proper, the engineer landfill site, at least how to design this, the barrier system, like clay liners, geomembrane. They are a combination of the different, because we have a lot of technology in these days. You don't worry about the technology, but we are worried about how to integrate these things in our engineering. It's a very important thing. And how to operate these things properly is another important things. What we are missing right now. This is the existing landfill site we have already developed in the municipality of Nepal. This is like one of the examples of Nepal guns. But we have a very proper barrier system, very good leachate collection system. Now finally, if you have not a good operation practices, this again is converted to the dump site, and many cases already happen in our municipality. This is the pity part. Yeah, this is one example. Recently, Bansari Dara, everyone knows this name in this day for any field of the people. This is the Bansari Dara. We have designed properly. We have a very good clay liners, geomembrane, and everything is there. Very good drainage system. But you see, now finally when you start to operate, you don't follow these operational guidelines as per the engineering landfills or guidelines. Then it's finally converted to the dump site. Again, another problem is happening there. The all leachate is going to the river system or ultimately in groundwater system. I'm talking about this monitoring and utilization land. Of course, this is a very important thing. We have to think, when you're talking about the sanitary landfill site, you have to think about the post-closure plan also before 20 years back. How to utilize this land, how to monitor continuously this gas and other water quality parameter after the post-closure. Then these things are very important. I'm not going to detail about this. And finally, I want to say something here. The first thing, we have to, this gradually change this our open dumping practice. Almost 90% of our municipality dump the waste. And we have to convert this dump site to the gradually from control to the engineer landfill and ideally the sanitary landfill. As an engineer, I would say the engineer landfill at least. But not only site selection, not only design, we develop is not only important things. The another things you have to think about the operational practice also. My today's talk is focus on how to dump site convert it to the engineer landfill because of this, the combination of the knowledge of hydrogeologists, geotech, and all the soil scientists, environmentalists. But we started to do it, but finally we failed again because of the poor operational practices. The good sanitary landfill ultimately converted to the open dump. That's why we have to work in vice versa. We have to talk about but as waste management students, landfill is not only a solution, I have to say, because this is the Hydrogeological Forum and all are the geoscientists, then I'm focusing only in this topic about how to convert. This is the last resort of the, the waste. That's why we have to start from this point. But landfill is the only venue where at least not more than 30% waste have to be, disposed there. 70% or more than 70% have to be recovered and treated as resources or raw materials. We can be done. This is we have a lot of technology. Having said that, I'm not going to, because I've already over the time, yeah? That's why I'm not reading all this conclusion. This is the bottom line, what I already mentioned. Having said that, we have to stop our degrading our water from mountain to the Tarai. Even in the Everest, Mount Everest, you have already read the news. There are the microplastic in the ice core because we have started, because this is almost 4,000 meter altitude. We have like the waste there. If we don't have a good collection and transportation system, ultimately this degrade there or spread there and finally go to the either our water system and other, if you burn, go to the your system. Then all that, one of the major polluters. Then we started the pollution from Everest to the city area. That's why the waste doesn't mean that the only is related to the urbanization, is not only related to the urban centers. It's all about, like in these days we're talking about the marine pollution and marine plastic. Even where the landlocked country, so many experts are working in marine plastic pollution, working on the marine plastic pollution, but we are not talking about the mountain plastic. Our mountain, our Everest are full of the plastic, has already become like dump site. That we have to think about the mountain plastic. We have to think about this proper waste disposal. Then this is our duty of these geoscientists, or whatever it's like, hydrogeologists or geologists or engineering geologists, geotechnical, whatever your terminology you can use. All the, this knowledge can be combined to shift this dump practice to the at least engineer landfill side. Thank you very much. Thank you.
Any question? दुईटा प्रश्न मात्रै लिनु होला, समय अभाव छ.
Namaste and good afternoon. It's me, Samanda Kanel from NAS, geotechnical engineer. I just have a query, not a question actually. Our team has done some research regarding the contaminations and change in engineering, geotechnical engineering properties of a soil in a schistole. We found that the value of a K, coefficient of permeability, was reducing. And during our literature review, we found from very different literature that the K might changes. It suggests that K might increase or sometimes might decrease. So percolations may happen, or it may cause in the flash floods if there is no percolations of water during the rainy seasons. So this is just a query that what might be the reasons for that variations of a K. It might be sometimes increasing and sometimes decreasing due to the leachate of the landfills you talk about.
Yeah, I think in my knowledge, I think the clay is also one of the complex materials. Then a lot of minerals there, and you're talking about sometimes the K values decrease or sometimes increase. It depends on how many times you conducted, how long you research you done, also one part. Because based on one sample or few research, we cannot go in conclusion. But the bottom line of use of the clay here in the landfill system as a barrier, is as a this liner. That's why the main purpose of the use of the clay here to increase the K value. Sorry, to impermeability. Because clay have impermeable natures. And in the past, we don't have a height or the technology or the materials like geomembrane and other things. And at that times, at per site specific situation, at least the clay have the less permeability value, and we can use as a barrier system. But in these days, we can use other materials. There are so combination of the different materials. We have a very impermeable in the natures to replace in the clay. I think this also was solution is such a level of confusion. But I'm not sure the leachate, because of the leachate, the K value sometimes decrease or increase. In my knowledge, I'm not sure about to say it happens. But of course, the clay is used here to decrease this K value. This is the bottom line of this, this liner system.
Anybody else? One more question. Okay. Yes.
Thank you, Dr. Pathak, for your nice presentation. I am Subodh Dakal from Department of Geology, Tirijana campus. Just a query, because I'm not much aware about this. So do you have something like integrated monitoring system for engineer landfill site or whatever landfill site currently in Nepal, so that we understand that what is happening, and then we use those knowledge for the future landfill site investigations?
Yeah, thank you, sir. But at least I already mentioned about some regarding the monitoring system. At least we have established the groundwater monitoring well, not all the sensor-like devices to monitor like gases and other things. At least we have established the groundwater monitoring well at the upstream. At least the two. Fundamentally, you have to do this theoretically. Then in many cases we have done. For example, even like Sistole is converted like to the dump site. Initially, when we designed and started to operate as a sanitary landfill, we have two groundwater monitoring well, one in the upstream and in the downstream. And we have a provision to measure the groundwater quality in every 6 months or in at least 1 year, depending upon your resources. Then you can identify whether our various systems work or not because of with the monitoring information from the monitoring well. At least we have installed this groundwater monitoring well. Except this, we don't have other devices to monitoring the other parameters. But you see, just it works for 6 months or 1 year. After then, you convert to the dump site, and nobody's care about whether the well or not. This is the problem.
Okay, धन्यवाद. वास्तवमा यो हाम्रो कल्चर, हाम्रो जुन नेपालीको कल्चर छ नि, त्यो कल्चरसित रिलेटेड धेरै इस्युहरू छन्. यसमा चाहिँ प्रेजेन्टेसन डीआर पाठकजीले जुन गर्नुभयो, यो प्रेजेन्टेसन वास्तवमा हामीले सिरियसली सोच्नुपर्ने अवस्था छ. यसलाई चाहिँ कस्तो छ भने अब यो हाम्रो काठमाडौँको नजिक भएको हुनाले र मेजर इस्युको रूपमा रहेको हुनाले यो सिस्डोलको जुन ल्यान्डफिलको इस्यु आइरहेछ, यसलाई चाहिँ सोसियली र पोलिटिकली धेरै इस्युको रूपमा लिएको छ. टेक्निकली अब इन्जिनियर्ड ल्यान्डफिल साइटको कुरा नि भर्खर हामीले सुन्यौँ होइन, ल्यान्डफिल मात्रै भनिन्छ. एनिवे जुन इस्यु रेज गर्नुभएको छ, सिरियसली हाम्रो जो सिभिलाइजेसनको लागि समस्याको रूपमा आउन सक्ने समस्याहरू छन्. ओके, नेक्स्ट प्रेजेन्टेसनमा थोरै जम्प भएको छ. हामी यो थर्ड प्रेजेन्टेसनमा नगएर चौथो प्रेजेन्टेसनमा सचिना नेवानीजीको प्रेजेन्टेसन छ. उहाँको प्रेजेन्टेसनको लागि म उहाँलाई कल गर्छु. प्लिज सचिनाजी, तपाईँ हुनुहुन्छ यहाँ? सचिनाजी, यस, ओके.
Good afternoon, everyone. It's an honor to be a part of first Nepal Hydrogeological Conference. Today I'm here presenting on the topic assessment of shallow tube wells using in situ physico-chemical parameters along Karnali-Gerwa river corridor system, western Nepal. moving towards introduction, as this program is mainly based on groundwater, my topic is also related to groundwater, and all we know that groundwater is a vital water source in lower Karnali Basin as well as all Tarai plains of Nepal. Shallow wells are widely distributed in Karnali lower basin that extends from Chisapani to Nepal-India border, which is the main source of drinking water, irrigation as well as ecosystem, because my study area lies in Bardia National Park. So groundwater can be one of the most important source of water for animal as well. So going towards my study, I have focused in situ physico-chemical parameters, mostly pH, AC, TDS, DO, and ORP. So dissolved oxygen and ORP are key indicators of redox condition in the study area. Field measurement provide rapid assessment for the groundwater parameters, where chemical tests are costly and it takes time to measure. So moving towards introduction slide, the total sample I have collected was 72, which we focused on shallow well, that were 56. River water samples were collected for the comparative study from groundwater and surface water. Similarly, shallow well samples, which is the key focus of the study, deep well samples were collected to compare the water chemical parameters of shallow well towards deep tube well. Similarly, canal water samples were also collected for the comparative analysis of river water, canal water, groundwater, and deep tube well water. So geographic coverage of the study area, as I have already mentioned, is from lower Karnali river basin, that has extends from Chisapani station towards Nepal-India border, following Karnali-Gerua river corridor. The study was conducted focusing on the pre-monsoon season epic dry period of the So main objective of this study was to conduct detailed well inventory along lower Karnali Basin, to measure in situ physico-chemical parameters of the study area, and to collect groundwater samples for detailed laboratory analysis. This is the study area, which represents the location where we have done well inventory and sample collection. The study area is geologically composed of alluvial deposits, and the study focused on spatial variability and redox sensitive condition in the study area. So methodological analysis for the study was, first of all, well inventory was conducted. Then on the basis of well inventory, samples were collected from representative wells, rivers, as well as canals. So different equipments were used, which are described here. The key observation of the study was in situ measurements showed active redox reaction. Rapid transformation of iron was observed in the sample, which were observed after sampling. The color has been changed, which is the key observation of this study. Certain wells exhibited highly reactive geochemical condition that is associated with health risks of both humans and animals. This is the key observation. We can see sampling bottle which has changed in the color of water samples, and similarly the next is tube well which has been rusted with iron. The color has been changed. So this can be one of the key observations from the study. These are the comparative analysis of all 5 parameters, pH, AC, TDS, DO, and ORP, which are shown in histogram. Similarly, analysis of all 4 parameters can be described by box and whisker plot, which represents the mean value and the outliers as presented in the figure. In the same way, parameters are distributed on the basis of geographical location, that is, more visible parameters can be observed in the southern part, followed by central part and northern part. So precipitation existed in southern part when we move from Chisapani towards Nepal-India border. The map represents the spatial distribution of all 4 parameters on the basis of latitude and longitude. So the color separates the distribution of parameters throughout the study area, which represents the spatial variation of the samples. Moving towards this slide, it represents the comparison of electrical conductivity and total dissolved solids. The first figure represents the comparative analysis of TDS and EC. Here we can see that TDS and EC has linear relationship with each other. Similarly, comparison of DO and ORP on the basis of highest and lowest values in the study area. So basically, DO and ORP are not related with each other. It shows variation in positive as well as negative basis. The figure represents the overall correlation of 5 parameters in the study area, where TDS and EC are highly correlated. Other parameters don't have significant correlation with each other. The main focus of this study is ORP distribution, as it shows immediate changes in the sample and color we have collected. So in shale wells, generally ORP has shown redox condition. Massive changes in redox ORP values has been observed, that is starting from some positive indicator to massive indication of minus 193. That means groundwater has basic redox reaction which can be effective to human health. Overall interpretation signifies that reducing shallow zones of may mobilize because of iron, manganese, and arsenic. So basically, arsenic can be tested in lab, but by the change in color, we can assume that the sample is presence of iron content, which has gone basic redox reaction. So in conclusion, ORP reveals redox variability across water sources along Cornali area. So shallow wells are most vulnerable to people, as it is the main source of drinking water to the people living near Cornali and Gerua river corridor. So practical field monitoring can give safe groundwater use in floodplain settings, not in Cornali river basin, but overall throughout the Tarai plain of Nepal. Thank you.
कुनै प्रश्न छ भने दुईटा प्रश्न जति लिन सकिन्छ. ओके, धन्यवाद सचिन जी. मलाई लाग्छ प्रश्न नभएपछि हजुरलाई प्रेजेन्टेसनको लागि धेरै धेरै धन्यवाद. स्टडी राम्रो छ. नेक्स्ट प्रेजेन्टेसन आर मल्ला एन्ड एस पाठक आउनुभएको छ. प्लिज. R. Malla, S. Pathak, and L. Pathak, Hydrogeological and Microbial Dynamics of Groundwater and Surface Water Interaction in Pokhara Valley, Nepal. Slide ready छ उहाँको सुरु गर्दा हुन्छ मल्लिजी
Namaste. So I'm Ravin Malla. I represent Center of Research for Environment, Energy and Water. This work has been carried out by my other two colleagues also, Sarad Pathak and Lalit Pathak too. So I'll be presenting this work, and this work was actually been carried out in Pokhara Valley. So it was a study been assigned by the JICA project through Yachio Engineering Company in Japan. So we supported them in carrying out this survey for the 3 types of water sources in Pokhara. So the groundwater water sources, deep and shallow, river water, all the 4 rivers, major rivers in Pokhara, and one of the lake, Phewa Lake, and also there were the drainage channel also and the dumping site also, but we haven't included those 2 types of water sources. So this is a hydrogeological and a microbial dynamics of water, groundwater and surface water interactions in Pokhara Valley. So we tried to, actually this was not the real the assigned title, but we modified it based on the data we had. So we're trying to, just align to this topic. So we know that we're aware about the Pokhara, and it's very popular both nationally and internationally. It's a hub for tourists, and there are many kind of, it's a valley, and there are 9 clusters of lakes also, and many rivers flowing through the valley. So there is a challenge of the urbanization rate is very high. So because of that, there is a stress on the many kind of the resources like water, lake water, river water, and all kind of natural resources are being stressed due to the urbanization and increase in population. And because of that, so with this, there is growing contamination, environmental issues because of discharge of the wastewater, dumping of waste, and all those kind of things are increasing the pressure on the environment also. So that is degrading the water sources also. So even in, not only in Pokhara, so even in Nepal, we have in Kathmandu Valley and many other places, we have this kind of issues of impact of urbanization and the environment stress on the water resources. So, but compared to the Kathmandu Valley in Pokhara, relatively the studies are not so much. So there is a big gap even in the water, in the assessment of the water quality of the various sources, and also the hydrogeological assessment of those groundwater resources also. So with this, we try to use that assignment information to to study, to analyze the this kind of issues. This slide is mainly, focused on it's related to like what is the impact of because of the climate change and also the increased population, increased urbanization rate, and it has on the water sources. For example, due to the increased discharge of wastewater, sewage, and that will amplify the increase in the microbial contamination. For example, the fecal contamination because of the increased water of rainfall and the increased temperature, that will just elevate the contamination of the microbial contamination in various sources. And that has been even indicated by the IPCC report. In the future scenarios also they have shown such kind of increased contamination due to climate change. So I think this slide is also very relevant to our study also here. So I use this slide here as a background. So the study objectives were like to investigate the seasonal hydrogeochemical and microbial characteristics of the water sources, and to know the pollution of the water sources and their risks to the environment as well as to the human being also, and to know the connectivity of the surface water and the groundwater. So we try to fulfill this objective in this study. So the study area is the Kathmandu Valley, mainly focused on in Pokhara Valley, mainly focused on the metropolitan area. So we had the three kind of water sources, groundwater. So we had 8 groundwater samples, 8 groundwater sites. So 5 were the deep groundwater sources, 3 were the shallow groundwater sources, and we had 4 rivers, Seti, Harpan, Fusre, and Furke rivers. So 4 rivers with 3 sampling points from upstream to downstream. And the lake was Phewa Lake. We had 5 sampling points. And we had the 2 years, dry season in the first year and wet season. And similarly, again in the second year, we had wet season and dry season. So total 25 sampling sites. So that makes around 100 water samples in both dry and wet for 2 years. The water quality parameters we analyzed were mainly 10 parameters. The physical-chemical parameters were water temperature, pH, EC, and the suspended solids, DO, BOD, COD, and for the nutrient, we had the ammonium phosphate, and for the microbiology parameter, we had the E. coli as a fecal indicator. So we carried out the statistical analysis, mainly descriptive analysis of the data, and we did the principal component analysis and the cluster analysis also. So this is the overall mean, standard deviation, and minimum and maximum values for all the parameters, for all the groundwater, river water, and the lake. So here, mainly I want to focus on, like if you see the suspended solids, the rivers is very high. You can see here this value. And for the BOD and COD is high in the river water and also lake. And for this is very interesting one, I think, the equally. You can see here in the groundwater, the minimum CFU, coliform forming units. So it's 1 and maximum is 1200. So very highly contaminated with the equally. Similarly, in all kind of water sources, like river also, it's very similar. And even in the lake water. So main here the groundwater sources are being contaminated, both shallow and deep. So it's mainly in the wet season we have found it. So in compared to dry, wet season is highly contaminated with the E. coli contamination. So this is just mean of the mean and standard deviation parameters. It's not easy. So here in this plot, we just did the spatial distribution of the E. coli contamination and the concentration. So here the mean, as I already just mentioned, that so all the water sources, river water, lake, and the groundwater sources are contaminated with the E. coli. You can see here the concentration. So it's very high for the river water, followed by the lake and the groundwater. So here I used the contamination, mainly the groundwater location at G3, G5, and the shallow waters, they are mainly contaminated with the E. coli. So I'm highlighting the groundwater pollution from the microbial contamination. So what we can say here that from the the groundwater mineralization is very high. You can see here the mean is 180, and so microsiemens per centimeter, and the pH is 6.9 to 7.9, and we have the nutrient is total nitrogen, total phosphorus is quite low. But the contamination from the E. coli, microbial contamination, is very high. You can see the maximum is like 292 CFU per 100 ml. So this indicates that the groundwater is being, is contaminated with the E. coli, and there is also mineralization also high. And the surface water sources, they displayed the seasonal extremes. So, for example, in case of the parameter suspended solids, especially in the river, all the river samples, in the wet season, that's during the rainy season, monsoon time, we have very high suspended solids in the water sources of the river, and similarly, even the equally also. So this is the correlation coefficient. So you can see here there is a very high negative correlation of temperature with suspended solid, ammonia, and phosphate. And also EC, lateral conductivity, and DO. And for the BOD and COD is positive. Similarly, for even the total phosphorus and total nitrogen also positive. So this trend, this kind of correlation is obvious. So it is as per the this is the correlation coefficient for the wet season. So in this also we have the similar correlation. If you compare with the earlier slide, that was the dry season, and this is the wet season, we have this similar kind of correlation with the parameters. So here, for example, I would like to say, in case this one, the suspended solids versus ammonia and the equally, so positive. So in the wet season, this value, this correlation also indicates that, if the increased suspended solids in the with the increase in the suspended solids in the water, the river water, we have seen that there is increase in the equally contamination, because that acts as a attaching material. So in this slide is the principal component analysis. So we have mainly the two components, and the total variance in the component 1 and 2 is almost 30 and 20. So of the total 100% variance, the explained variance is 30 and 20. So in that, so we have the three clusters. If you see here, the cluster 1, these are the river, this is the lake, and this is the river. So the river and the lake in the cluster 1. So in the cluster 2, we have the groundwater, and it's both the deep and shallow, and cluster 3 is the this river and few groundwater sites. So in this also we have the very similar kind of variance is almost similar of the two principal components. So in this also we have these three clusters, similar to the earlier slide season. We have these are all the rivers and lakes. Here also we have the groundwater and the shallow groundwater, and this is the cluster of one of the river, Harpan. Okay, so with the conclusion, can say that the microbial contamination, we have found it in the groundwater sources, so that indicates the vulnerability of the such kind of water sources, and this also indicates that the groundwater contamination might be, from the surface water that leaches to the groundwater layers. So we can draw this conclusion, and another is like hydrogeological insights. The principal component analysis is revealed that there is a transitional groundwater mixing. That in groundwater sites number 4, 2, and 3. So it indicates there is localized groundwater leaching in the surface water source. From the surface water sources, there is leaching of the water to the groundwater sources. And the seasonal influence, we have found that mainly, especially in case of the E. coli and suspended solids, so there is a significant, notable type of seasonal influence. So that increase the groundwater contamination also, and you can also see the recharge of the groundwater from the surface water. And so I would like to, as a way forward, this study was as part of our assignment, and we also like to, after this, to supplement this study. For example, we didn't have the data for like the ions to make a detailed study about the hydrogeochemistry. So in this next study, we have the hydrogeochemistry of the groundwater and also the estimation of the recharge. So these two aspects of the study, we already have conducted the study, and the results are in the pipeline. So this study can be complemented from this next our work. So in that study, we will have more on the hydrogeological chemistry and also the recharge estimation of the Pokhara Valley. So this is as a way forward. So with this, I would like to end this my presentation, and I would like to acknowledge the HGO Engineering company and the Nepal Water Supply Corporation, Pokhara office, FEWA, Lake Boating Association, and the households and the industries, that they gave us the access to their water sources, and they supported this survey also. Thank you.
धन्यवाद रविन्द्र सर. कुनै प्रश्नहरू, कुनै क्वेसन? ओके, यो धेरै ढिलो पनि भयो, अनि यो सेसनमा विशेष गरी यो ग्राउन्ड वाटर क्वालिटी सम्बन्धी भएको हुनाले एउटा मेरो अब्जर्भेसन के भने जति बुझ्यो उतै डर लाग्दो छ सिनारियो के. तर अब रिसर्चको पार्ट भएको हुनाले जे आउट फाइन्डिङ आयो त्यसमा चाहिँ अब पोलिसी मेकरहरूले ध्यान दिनुपर्ने कुरो, रिसर्च गर्नेले त रियलिस्टिक कुरा चाहिँ फाइन्ड आउट गरेर पब्लिकमा ल्याइदिने हो. त्यस कारणले धन्यवाद प्रस्तुताको लागि. 6वटा प्रस्तुति मध्येमा एउटा चाहिँ प्रस्तुत हुन सकेन, र अमेरिका र इन्डियाबाट पनि 2टा प्रस्तुत भयो. त्यसमा पनि के इस्युहरू चाहिँ ग्राउन्ड वाटर कन्टामिनेसनका इस्युहरू र मेन मेड कन्टामिनेसनका इस्युहरू चाहिँ रेज भएको छन्. मलाई लाग्छ आजको यो प्रस्तुतिबाट चाहिँ केही हामीलाई चाहिँ दिशानिर्देशन गर्नको लागि पोलिसी मेकरको लागि केही चाहिँ सपोर्ट हुनेछ. यो प्रस्तुतिमा चाहिँ प्रस्तुत गर्ने सम्पूर्ण चाहिँ प्रस्तुताहरूलाई म धन्यवाद दिन चाहन्छु. सँगसँगै मेरो मित्र रिपोर्टर स्वर्ण साक्यजीलाई पनि धन्यवाद दिन चाहन्छु, र सँगसँगै प्रस्तुत मा क्वेसन गरिदिने साथीहरूलाई पनि धन्यवाद छ। सँगसँगै यहाँहरूले यति ध्यान दिएर सुनिदिनु भएकोमा पुनः सबैलाई धन्यवाद दिँदै यो सेसन यहीँ अन्त भएको जानकारी गराउन चाहन्छु र आयोजकले मलाई सूचना गरिसक्नु छ लन्च तयार छ, कृपया लन्च लिनु होला। धन्यवाद सबैलाई पुनः।
Thank you, Narendra sir, for the chairing the technical session first. हामीले चाहिँ rapporteurs र token of love वितरण गर्ने कार्यक्रम रहेको छ। म token of love वितरण गरिदिनु हुन यस संस्थाका उपाध्यक्ष आदरणीय खिलानाथ दाहाल सरलाई अनुरोध गर्दछु र token of love लिदिनु हुन यस सेसनका चेयर मिस्टर नरेन्द्र खत्री सरलाई म अनुरोध गर्दछु। लाइट बाल्दिउँ न ल, लाइट कहाँबाट? त्यसैगरी यस टेक्निकल सेसन फर्स्ट का र्याप्टर्स मिस्टर श्रवण साक्य सरलाई पनि टोकन अफ लभ वितरण लिदिनु हुन अनुरोध गर्छु। र हाम्रो यो टेक्निकल सेसन फर्स्ट सम्पन्न भएको छ। अबको आधी घण्टापछि हामी टेक्निकल सेसन सेकेन्ड सुरु गर्नेछौँ। त्यसको टपिक रहेको छ ग्राउन्ड वाटर सस्टेनेबिलिटी पोलिसी एन्ड म्यानेजमेन्ट। सम्पूर्ण उपस्थित महानुभावहरूलाई आफ्नो लन्च लिनको लागि माथि हलमा प्रवेश गरिदिनु हुन अनुरोध गर्छु। धन्यवाद।